Welcome back to Basic Electronics. In the previous lecture, we looked at the op-amp buffer as a special case of the non-inverting amplifier. In this lecture, we will see the meaning of the term loading effects and see how an op-amp buffer can be used to eliminate these loading effects. We will then look at another useful op-amp circuit, the summer, which can be used to add two or more input voltages. We will illustrate the operation of the summer with the help of simulation results. We will then comment on the range of resistance values that are commonly used in op-amp circuits. Finally, we will present an op-amp circuit, an amplifier circuit, which allows a relatively large gain without using large resistance values. Okay, so let us begin. Okay, so here is a summary of the op-amp buffer. This is the circuit. We have a source on one side and we have a load resistor on the other side. The input resistance of the op-amp buffer is the resistance we see from here, and the output resistance is the resistance we see from here. And we have seen that the input resistance is very large, almost infinite, and therefore in the equivalent circuit of the buffer we can show an infinite resistance here, which is an open circuit. We have also seen that the output resistance of the op-amp buffer is very small, almost zero, and therefore we have shown a 0 ohm resistance here, which is a short circuit. We have also seen that the gain of the buffer is just 1, and therefore if this voltage is Vs, this AV times Vi is simply Vs. So that is the equivalent circuit of the op-amp buffer. And to summarize, it provides a large input resistance as seen from the source, a small output resistance Rout as seen from the load, and a gain of 1, that is the output voltage simply follows the input voltage. We now return to our original problem. We have a source with source voltage Vs, source resistance Rs. Our load resistance is RL. We want to apply an amplified Vs across RL, and this is the amplifier we want to use, which has a voltage gain of AV. So what we would like is VO to be equal to AV times Vs. Now if you recall, with this configuration, the output voltage is not AV times Vs but something smaller, AV times RL divided by RO plus RL, and this factor arises because of the voltage division happening here on the load side, times Ri divided by Ri plus Rs, where this factor is because of voltage division happening on the source side, that multiplied by Vs. So it is not quite what we want. What we want is VO equal to AV times Vs. And now let us see how we can use an op-amp buffer to achieve this target. So this is how we can use an op-amp buffer, one on the source side and one on the load side, to obtain VO equal to AV times Vs and eliminate the loading effects on the load side as well as on the source side. So this part is our source as before. This is the amplifier and this is the load. What we have done is, on the source side, between the source and the amplifier, we have inserted one buffer circuit. Similarly, on the output side, between the amplifier and the load, we have inserted another op-amp buffer. And let us see what this does. Since the buffer has a large input resistance, I1 is 0, this current, therefore no voltage drop here, and V plus is the same as Vs.
Now for the buffer, the output voltage is the same as the input voltage. So therefore VO1 is equal to this voltage here, which is Vs. Now let's come to the load side. I2, this current, is also 0 because the buffer has a large input resistance. Therefore no voltage drop here, and VO2 is equal to AV times VI. VI here is this voltage, which is VO1, equal to Vs. That gives us VO2 equal to AV times Vs. And VO is the same as VO2, and therefore we get VO is equal to AV times Vs as we wanted. And that is irrespective of Rs and RL, because we did not have a voltage division on the source side or on the load side. Let us note that the load current is supplied by the second buffer. So the load current is really coming like this, and that acts as a voltage source equal to AV times Vs with zero source resistance. Why zero source resistance? Because that's a buffer, and as we have seen, the buffer has a very small output resistance. So this is how a buffer can be used. Whenever we are concerned about loading effects, we can insert a buffer, and that essentially eliminates the loading effects. So when we started off, we got VO equal to VI for the buffer, and it was not clear whether that is at all a useful relationship, because we are simply getting VO equal to VI. But now it should be clear that a buffer really has a very important role to play in electronics when we want to isolate the source from the load. Here is another commonly used op-amp circuit, and in fact we are already somewhat familiar with this circuit. Imagine that we don't have this R2 and R3, and in that case the circuit reduces to the inverting amplifier that we have seen earlier. Alright, now coming back to this circuit, there are three inputs here, VI1, VI2 and VI3. That of course is the output. And now let us see how this circuit works. We will assume that the op-amp is operating in the linear region, and therefore V minus and V plus are nearly equal. So we have V minus equal to 0. What would this current be then? I1, it would be VI1 minus 0 divided by R1. What about I2? It would be VI2 minus 0 divided by R2, and so on. So we have these three currents now, I1 equal to VI1 by R1, I2 equal to VI2 by R2, and I3 equal to VI3 by R3. Next, because of the large input resistance of the op-amp, II, this current, is 0, and therefore we can say that IF is equal to I. And once we know IF, we can obtain the output voltage VO, which is V minus this voltage drop. V minus is 0, and IF is the same as I, this expression here. So then putting it together, we get VO equal to minus RF by R1 times VI1 plus RF by R2 times VI2 plus RF by R3 times VI3. Now this we can think of as K1 times VI1 plus K2 times VI2 plus K3 times VI3, where we can adjust K1, K2, K3 by simply choosing the values of R1, R2 and R3. So this circuit is in fact doing a weighted sum of VI1, VI2 and VI3, and the weights K1, K2, K3 can be adjusted using the resistances. And if we make R1, R2 and R3 all equal, denoted by R, then we have minus Rf over R Vi1 plus Rf over R Vi2 plus Rf over R Vi3. So that Rf over R is a common factor. We can take that out and then get minus K times Vi1 plus Vi2 plus Vi3. So this is simply a summer circuit. It is simply adding 3 voltages. In fact, we can extend it to 4 voltages if we like by adding another resistance, or we can have just 2 voltages, Vi1 and Vi2. So there is some flexibility in configuring it appropriately. Here is an example. The circuit file is also available, so you can check out this simulation and change the input voltages or resistance values and so on. What we have here is 3 voltages, Vi1, which is a constant DC voltage 1 volt, Vi2 is a sinusoid, Vi3 also a sinusoid with a lower amplitude and higher frequency as compared to Vi2. The resistance values R1, R2, R3 are chosen to be equal 1K, and RF is chosen to be 2K. So if we substitute these values in our previous expression, we end up with VO equal to minus 2 times Vi1 plus Vi2 plus Vi3. Let us look at the output voltage waveform now. This one. We see that there is this low frequency component, and that comes from Vi2, and superimposed on that we have this high frequency component, and that comes from Vi3. And notice that this entire waveform has been shifted such that it has an average value of about minus 2 volts, and that comes from Vi1. And it is easy to see where this minus 2 volts is coming from. We have Vi1 equal to 1 volt, and that 1 volt gets multiplied by minus 2 here, and that gives us minus 2 volts. Alright, now let us make a few important points. Note that the summer also works with DC inputs. This is a DC input, for example, and that comment applies also to the inverting and non-inverting amplifiers. These circuits would also work with a DC input. And compare that with the common emitter amplifier we have seen before. In the common emitter amplifier, if you recall, we had a coupling capacitor which connected the input voltage to the amplifier. And if the input voltage is a DC voltage, then this coupling capacitor would block that input voltage, because the entire DC input voltage would appear across the coupling capacitor, and the amplifier will not even see that DC voltage, and therefore it will have no impact on the output of the amplifier. So in that sense, these op-amp circuits are definitely better because they can be used for DC voltages or slowly varying voltages, whereas the common emitter amplifier cannot be used for those conditions. Second point, op-amps make life simpler, and this is something that should be obvious by now. For example, if we think of adding voltages in any other way, we will find that it is not at all trivial, whereas this circuit, the summer, makes it very easy. And not only that, it even allows us to vary the weights for these 3 input voltages by simply changing these resistance values. Let us now talk about the choice of resistance values in op-amp circuits. And this is a very important question from a practical perspective. If we want to build an op-amp circuit, we will definitely need to know whether any arbitrary resistance value is good enough or there is some restriction. Turns out that there are some restrictions, and let us see why. If the resistance values are too small, for example, then they draw larger currents. And where do these currents come from? They eventually come from the power supply, that is VCC and minus VEE. And that leads to an increase in the power dissipation. And that, of course, is in general undesirable. What if the resistance values are too large? Let us see what happens in that case. 1. The effect of offset voltage and input bias currents becomes more pronounced, and this is something we have not yet discussed. We will look at it soon. In short, what happens is the circuit performance is then not what we would expect, and that of course is not desirable. Second, combined with parasitic or wiring capacitances, large resistances can affect the frequency response and stability of the circuit. To give an example, say we connect an op-amp amplifier circuit and give certain input voltage and expect a certain output voltage. Now we connect our output to the oscilloscope and find that there are some oscillations at the output which have nothing to do with the input voltage. Now this kind of situation can arise if the circuit is unstable, and that can happen if the resistances are very large, and therefore those should be avoided. Third, there is something called thermal noise. What is the meaning of noise? Noise is a kind of disturbance that rides on our signal voltages, and it is something that we don't want because that corrupts our signal. Now this thermal noise increases as the resistance value increases, and it may not be desirable in some applications. So because of all of these considerations, very small resistance values and very large resistance values are avoided in practice, and the typical resistance values which we use in op-amp circuits are in the range 0.1K to 100K. So if we are designing an op-amp circuit, we should make sure in general that our resistance values fall in this range. Let us do this design problem. We want to design an amplifier with Rin equal to 10K, the input resistance of the amplifier, and a voltage gain of minus 100. We have already seen an op-amp circuit, the inverting amplifier, which gives us negative gains. So we can choose that. The input resistance should be 10K of this amplifier. So let us see what that gives us. What is Rin is the same as R1 prime as we have seen earlier, and that happens because the inverting terminal is at virtual ground and this current is VI by R1 prime. So that gives us an input resistance of R1 prime. Since Rin is supposed to be 10K, we have to have R1 prime equal to 10K. What about R2 prime? That is given by the gain now. Since the voltage gain of the inverting amplifier is minus R2 prime by R1 prime, and that we want to be minus 100, that gives us R2 prime. So R2 prime should be 100 times R1 prime, which is 10K. So that comes to 1 mega ohm. And as we saw in the last slide, this value is somewhat large and it may be unacceptable from practical considerations. So therefore this solution is certainly not the best. So let us see if we can improve on that. So we need a design which has smaller resistance values. Fortunately for us, electronics is full of clever tricks, and here is one of them. So we modify the circuit. We put a black box here instead of R2 prime. And what should that black box do? The same thing as what R2 prime does here. What does R2 prime do? If I call this voltage V1, this is of course the virtual ground, and this current as I1, then V1 divided by I1 should be R2 prime, which is 1 meg. So in this black box, we should ensure that V1 divided by I1 is the same value, that is 1 meg. But the network inside should be designed so that it does not use large resistance values. So let us see how that can be done. Let us consider this T network as called T because it looks like the letter T. It consists of three resistances, R1, R2 and R3. So this is going to be our black box that we saw in the last slide. And what we want from this black box is V1 divided by I1 is 1 meg. So let us first see what V1 over I1 is in terms of R1, R2 and R3. Let us look at I2 first. Now in this circuit, R1 and R2 are actually in parallel because this node is common and that other node is also common. Therefore, the net resistance seen from here is R3 plus R1 parallel R2. So therefore, I2 is V1 divided by R3 plus R1 parallel R2. Let us now look at I1, that current. Once we know I2, we can obtain I1 by using the current division formula. So I1 is going to be R2 divided by R1 plus R2 times I2. And that gives us this expression for I1. Let us define R effective to be V1 by I1, and since we already have I1 in terms of V1 here, we can find V1 over I1, and we can see that this R1 plus R2 is going to cancel out, and we get V1 by I1 as R1 R2 plus R2 R3 plus R3 R1 divided by R2. And now our job is to choose R1, R2, R3 such that R effective, which corresponds to R2 prime in our previous slide, should be 1 meg. If we can do this without using large resistance values, then our design is done. So what we are going to do is replace our original inverting amplifier with this circuit, and the job of R2 prime is now being done by this T network, and our next step is to find R1, R2, R3, which will give us the same R effective as R2 prime, which is 1 meg. Here is our expression for R effective, and we want R effective to be 1 meg. So what we will do is take R1 and R3 to be equal, and we will call that R. Then in terms of R effective turns out to be this expression here, and we can now solve for R2 as R divided by R effective by R minus 2. For R equal to 10K, for example, R2 turns out to be 102 ohms. So in this manner, our objective of a gain of minus 100 is now achieved, and we have done that without using large resistances, and therefore our design is a good one. Now 102 ohms is not something that is readily available, so we would generally put a pot here and then adjust its value. By the way, this circuit is taken from this book here by Waite and others, and there are many other interesting op-amp circuits in that book, and you may take a look.
In conclusion, we have seen how an op-amp buffer can be used to avoid loading effects. We also looked at the op-amp summer and illustrated its functioning with the help of an example. We commented on the range of resistance values which are typically used in op-amp circuits. Finally, we looked at an interesting amplifier circuit which gives a relatively large gain without using very large resistance values. So that's all for now. See you next time.